where can we find information about God? I tried to share things about God with people different times and of different persuasions. And it all comes down, it seems, to hinging on whether or not you want to accept what this book says. And because they have their writings, and they believe those just as much as we believe the Bible. And so now you're left with a decision. What am I going to choose? That book or something else? Now there is another avenue whereby we may learn about God. I've alluded to that already today. In nature. Right, now could you imagine some person who has never heard of the Bible, and they look at nature and they watch the birds and they look at the animals, and you know, people of this type, they look at nature and they tend to work in harmony with nature. Now there must be something there that convicts them that there is some higher power somewhere that brought all these wonderful things into existence. Now when you talk to people who are of an evolutionary persuasion, they sometimes find it very hard to appreciate creation. But do you know that the largest growing minority group are scientists who previously were evolutionists? They are becoming creationists, or rather, may I say, believers in intelligent design. And what I want to share with you today is this on the screen here: God's signature, and it is DNA. What's that stand for? There it is, deoxyribonucleic acid. What's that? Man, I can't even pronounce it, let alone know what it is. What is it? Deoxyribonucleic acid. It's an acid of some sort, that is true. Now, in your body, there are cells, and those cells have what is called DNA in them. And that DNA holds a code which describes everything about you, all the physical functions of your body. When the two eggs meet right at conception, the sperm meets the ovum, and then you have the cell division, and eventually grows into a little babe, and eventually born and grows up to be a full-grown human being, and so on. The DNA will determine the features and the characteristics of the physical makeup of that person. Also carries certain details about your emotional and your mental capabilities as well. So that, you know, you might have a parent that is maybe a good artist, might be a good musician, might be a handy person in engineering, and the offspring will have a similar kind of talent or skill. And did you know also, you know the skill that God gave to many of the artisans that were doing the work in the sanctuary? Genetically, that has been passed on down through the years, and you find people today who are very gifted in that area. And I suppose if you trace it back, you'll find they're connected with those artisans of the early days. Now, there I've just shown a very crude illustration of the cells of your body, the building blocks of the tissue. And these things will control heredity and ensures that everything will be reproduced after its own kind. It says in Genesis that the cattle will reproduce after their kind, and the birds, etc., etc. And so now it's all done through the DNA. How does the DNA do this? Well, it's based on a code. Now you look at that sentence there at the top. How does the DNA store data? Would you believe that the next line has exactly the same characters in it, but you cannot understand it? Why? It is because they're all jumbled up, they're thrown in there in a haphazard random manner. Even though they're exactly the same characters, it means nothing to us. Now, this is a little bit like the DNA code. Not to say that it doesn't mean anything to us, we're learning some wonderful things. Back around the 1950s, I think it was, three fellas discovered the DNA molecule. And they received a Nobel Prize, that's it, yes, for their discovery. Now, a code can be anything. There's a three-tier code that you and I face every day, and it's made up of colours. Does anybody know what it is?
Traffic lights.
Traffic lights. That's simply a code. When the red one comes up, what does it mean? You're stopped. And so on. And so it's a code just the same as any other code. If I were to get, take a page out of my Bible here, and I were able to cut every little letter out of this and put them in a box, give it a shake up and throw it on the floor, what do you think might be the chances of it falling into a place so that it would look like that page? Impossible, right? And so now, all these letters, while they mean something to us, if they are not in the right order, it means nothing. But you get these letters in the right order, and they tell us a lot, do they not? And so now it's the same here with DNA. Do you know that DNA has enough information in it to fill about 600,000 pages? 600,000 pages. That's approximately, it's not hard to find books of around 500 and 600 pages. And so you're looking at, say, the library of around 1,000 books holding about the same information as what you would find on one DNA molecule. The DNA molecule, when it's a helix, right? A helix is like a spring. If I got a spring and I pulled it, it might only be about that long. But when I pull it out, it can come out to maybe that long. I think we all appreciate that. The helix of the DNA, it could stretch out. Now, mind you, a DNA is measured in terms of nanometers, right? Now, a nanometer is 10 to the minus 9 meters. What's 1,000?
Million.
Sorry, 1,000. It's a milli, right? And what's the next group of 3? 10 to the minus 6, which would be a micro, right? 10 to the minus 6. And then after that comes a nano, which is 10 to the minus 9. Then after that comes pico, which is 10 to the minus 12, right? That's far enough. And so we see that we get so small, that, and yet when it is stretched out, it can be about 400 millimeters long. So that is a remarkable thing. Now, the amount of data there is enormous. And in that data, it's able to describe every feature about you. And as we look through this, we're going to see some wonderful things of what your DNA does. Hopefully, now I'll tell you what, I'm relying 100% on God here because this is a complex subject. It's one of my pet subjects, and I don't purport to understand it fully. I hope, by the grace of God, that by the time we finish here, we will be able to understand it reasonably well from a layman's point of view. So now, what we want to do is to try and understand how the code is put together in the DNA. And these fellows that discovered it back in the 50s, they had a bit of an idea of how it went together. But we've learned some tremendous things about DNA since then. Okay, so it's an acid, and it exhibits acid properties, and so therefore it's called an acid. That makes sense. Now, there are 46 chromosomes, and on the now there's one DNA molecule. What have we got in mind there? 46 DNA molecules. Anyway, we'll move on to the next bit. So it's got all the information you want, and now there's one thing there that has intrigued me, and that is, you know, when you get that first egg separating, now you've got 2 little cells, and then you get 4 and 8 and so on. Eventually there comes a time when the cells need to change. For example, our body is made up of skin, blood, bones, various kinds of tissue. For example, the tissue of the lungs is different to the tissue of the heart, and you've got fingernails, etc. So you've got all these different things. How does the how does the dividing cells know that, right, I'm going to be a fingernail, right? And another one says, all right, well, I'm going to be some hair. That's an amazing thing. All that detail is in the code. Okay. So now looking at the DNA molecule, there it is shown as a helix, and all those little balls there, as it were, they are all molecules. Now, what's a molecule? A molecule is a collection of atoms. Right? Now, there are largely two kinds of materials. There are atoms, or there are elements, which are pure substances. And there are compounds, or molecules, if you like, which are combinations of elements. Give me an example of an element, a pure substance. Calcium, aluminium, platinum, oxygen, gold, etc. Right? So we've got the idea. Give me an example of a compound or a molecule. Water, salt, all right, sodium chloride, hydrochloric acid, and so on. All right, now, in the molecule of the DNA, we find that there is a molecule that looks like that. Now, that's a frightening looking monster, isn't it? Now, that there can be represented by that little section there. What I've tried to show is a block diagram which represents this molecule. It's made up of three parts. This part here depends upon a phosphorus atom, and this one here is a carbon atom. This one here is the base, or it is based on nitrogen. Now, there's a reason for that. Here, there's the phosphate molecule, there's the carbon molecule, and after all, sugar is just carbon, and there's the base. Now, there are four bases, and I'll go into that in a couple of minutes. Now, what happens is that the phosphate molecule on the adjacent DNA molecule, or the nucleotide as it is called, nucleotide, that there is a nucleotide, and it is made up of three molecules: phosphates, carbon, and nitrogen-based molecules. Down here I've shown a helix, if you can show a helix in two dimensions. Can you see there are two colours, just on that vertical there? Two colours. One is red, the other we'll call it black. The red one would represent the base. Across the top of the T here is the two phosphates, there and there. No, sorry, is the sugar. And then the black dots represent the phosphates. And now what the phosphates do is join these molecules end to end, or one piece by piece. And so now there they are, all linked together. There's one nucleotide, and there's the next, and there's the next, and they all join together and they form the chain. On the other side of the helix, or the spiral, is exactly the same thing, except for one thing. Notice this has a rather a funny looking shape. Well, I'm going to enlarge on that in a minute. We're going to see why it is that strange shape. There we have a whole lot of nucleotides now together. C, A, G, T, and so on. What that stands for is adenine, thymine, cytosine, and guanine. Just take the first letter of each of those and it is far less complicated. We're going to take the first letter just the same as I would take the letters out of the Bible, and I would cut them all up and make all these little characters and lay them all out, and I can make a message. Well, these letters enable us to make a message. Now, obviously, this machine doesn't read the letters. It looks at the chemical. All right. Just here you'll see we've got an A base, we have the sugar or the carbon, and then here and here we have phosphate. And the phosphates join us to the next one. And so now you'll notice here we have CAGT, and on the opposite side we have GTCA, and so on down here too. Look at the shapes of them. That one will only fit into that kind of a shape. That one will only fit into that kind of a shape, and so on. Notice here there's G and there's C, they're on the same side. And they will attract, or they will be connected to a base which is of the complementary shape. Does this sound complex? It does, doesn't it? I've had to go over this quite a number of times to understand it. Anyway, I'm hoping I'm going to try and be able to get it across as simply as I can. It looks complex as I'm just explaining this, but as we work through it, I hope it'll start to gel. And the reason why I want to have a look at this is because it is so complex that it cannot possibly evolve. You see, Charles Darwin, in his ignorance, went out to the Galapagos Islands and he started to have a look at all the little birds, and he'd come to a conclusion, well, it's these different birds have evolved into different, had different features, and so therefore that was the way all things have come into existence. Now what he also is on record as saying, I'm not quoting him verbatim, I'm simply going to try and paraphrase it. He says, if it can be proven that things are more complex than what I have purported them to be, it will destroy my theory completely. And that's exactly what we're going to look at here. You know that Charles Darwin had no idea about this. And so God says that in the last days, knowledge shall be increased. Now, knowledge being increased, this is part of it. And you can see the technology that is taking place in the world today is enormous. And God is bringing forth things to strengthen his people and to show the worldly wise person that they are foolishness in the way they reason things. God is bringing forth knowledge to enable us to vindicate his name. So now, these nucleotides are really the key to the data that is there. And as you can see, we're using letters, and that enables us to read these and to make some sense out of it. Alright, so this then being the two sides of the helix, we can see now that one side of the helix will be of one polarity, if you like, and the other side of the helix will be the complementary polarity, or the complementary shape. And so on it goes through the four different letters. There are four letters involved in this. In this, with these four letters, it will make up the code to tell the cell how to make another cell. You know, you've got all these cells dividing in your body, and from what I understand, it takes about 7 years, and it's a new you. All right, every cell in your body has been replaced. But anyway, let's move on. There's the helix now, and we see how all the nucleotides are all nicely married together. Every shape is nicely connected. Now here's something interesting. Notice it's like a zipper. Zoop, it's open. Now when that opens, we have this arrangement. Inside the cell, there are more of these little nucleotides floating around. Now you know, if I were to pick up a substance that is above 0 degrees, absolute, all right, that is above 0 degrees, you've got electrons floating around in there, and they're just free, separated from the atoms. You know what I'm talking about? All right. And so likewise, these things, these little fellas here, they're all drifting around in space inside the cell. And when this DNA molecule opens like this, the free nucleotides will connect with its complementary nucleotide on the DNA molecule. Now look what occurs. We now have this pair here made up, and we have another pair over here made up. Notice here, that one has been replaced with this one. And look at the shape of that one. It's been replaced with exactly the same shape. This one here has been replaced with the same shape. So now, by the time the whole 400 millimeters of the DNA molecule has unzipped and all the nucleotides that have been floating around in space of the cell have now joined themselves with the DNA, what have we got? We now have two of them. Each branch of the dual molecule, as it were, have now separated, and what have they done? What's happened? It's made a new one, hasn't it? It's made a new DNA molecule. Now we have how many? Two DNA molecules, a perfect replica of the original.
Father and Son.
Indeed, Father and Son. All right, so there we have this perfect replica. And there are certain, notice, look at the shapes of these. Could any other nucleotide marry up with that one? Only that one, right? This is something that has been built into this network, which is a safeguard against error. Look, you can imagine there are literally billions of codes in the DNA for a human being. There's about just under 600,000 code letters for an amoeba. What's an amoeba? An amoeba is a single cell living creature that lives in water. And it is so tiny. And it has more than 500,000 code letters making up its DNA. In us, you and me, it's billions. Like it's measured in terms of billions, 10 to the 9, all right? Or 1,000 million. And so now, what happens from there? Well, there we have this separation. Okay. Now, what happens is that when we've got, why would we want to separate or split the DNA? Why would we want to do that? Because what has to happen is that each cell has to replicate and keep you alive, right? It's got to keep going. Now, when a new cell is born or when they separate, what must be present in the new cell? DNA. Where does it come from? There. One for the parent cell and one for the child cell. All right. Now, mind you, you can't tell the difference between them. They look the same. But I'm simply saying the original and the new. And so now, here we have another thing now. We've seen now how that DNA is made up of nucleotides. Nucleotides are made up of three kinds of molecules. A phosphate molecule, a nitrogen molecule, and a carbon molecule, right? And so now, here we have another division taking place. When in order to make this new cell so that this cell is able to replicate or to duplicate itself, we now have a process called transcription. Now here we have the DNA or the DNA molecule. Now imagine if you were an architect and you just designed this building. It's a 50-story building and you just designed this thing and there it is all on the plans. Years work, all right? And the contractors come in and they want a set of the plans. What do you give them? What is it? A duplicate, would you give them the originals? No. Why? I might lose it. You wouldn't want that to happen, would you? These days with computers, the copy's on the computer. But anyway, and the DNA recognises the value, I beg your pardon, the cell realises the value of the DNA. We can't let this out of here, because if that gets lost, we've got problems. We can't duplicate ourselves. Right? And so now, what happens is that the DNA unzips a little bit, not entirely, but just a little portion of the string of nucleotides. Now here we've got 1, 2, 3, 4, 5, 6, 7, 8 of them have been opened up. What happens? As it turns out, there are 3 chemicals. There's the A, the C, the G and the T, right? There are 3 of those which make up the code from which the cell will manufacture proteins. What are your cells made of? Protein. That's why there's this big push about eating lots and lots of protein. Because your body actually manufactures it, would you believe? There's another thing too. What other kind of things does the nutritionist suggest that we get plenty of? Amino acids, right? A balance of amino acids so that our body is equipped to manufacture protein. And in fact, these here will attract nucleotides from which the code can be made up that the DNA can say, right, now I know how to make a protein. This thing is going to manufacture proteins using amino acids. Let's look and see how. All right, in this transcription, the DNA opens a little bit, not entirely. The duplication is now complete. So when it opens, it will then attract some of these free-floating nucleotides. And when it does that, and it is sufficient then, these will be released and they will drift into the, they will drift outside, eventually find their way outside the cell. In which place they will then go to a machine or to a section where it is able to say, okay, this protein we want to make is going to be made up of this amino acid and this amino acid and so on. It will then collect all these amino acids, put them together, and it will manufacture a protein atom, a molecule rather. That molecule will then go in to make its contribution to the building up of a new cell. And so, now, let's have a look at this little summary. DNA does not leave the cell, it is too valuable to risk damage. The DNA will unzip for a portion of the whole code relating to the protein required. It will unzip a little bit for the particular amino acid that it needs to manufacture a protein. Now I want to ask you a question. How does the DNA know what part to unzip, what direction to read, and which one of those nucleotides to start counting at? Interesting. All this is contained in the code. And it says, start here, unzip that much, read this bit only, take that data away and manufacture a protein. Now mind you, this is a code that has set this up. I want to ask you, let's just say things maybe could evolve. Speaking hypothetically. Let's just say it could evolve. That somehow things came together and things were constructed. Where would the code come from? What does the code suggest? If I got these characters and just threw them on the floor, how many times would I have to do it before I bring this page up again? It would never happen. But evolutionists are saying that the unbelievable complexity of this place just fell into place given sufficient time. Given that might be the case, where did all the characters come from? Why is it that these characters mean something when I see them fall on, oh look, I might be able to see a couple of words where they accidentally fall into place, but to get it to come together like this, which has the whole information in it, is impossible. Where did the code come from? A code suggests
intelligent design.
Intelligent design. You can't. What are those three colours that face you when you come to an intersection? It's intelligent design, is it not? So, DNA is God's fingerprint that laughs at the evolutionists because it cannot possibly evolve. Free nucleotides pair up with the exposed nucleotides. Looking from, that's the RNA. Now the RNA, remember I said it unzipped a little bit and then it took that print and then it sent that print away to the manufacturing department. Well, that little copy that goes away is called RNA, and that's the DNA. So that would associate with RNA, DNA, RNA, DNA. And so now what we see is that now there is a difference between the RNA and the DNA. One of the things that is different, notice I've got a U there. Did I mention anything about that's uracil? Did I mention anything about that before? No, I didn't. In the RNA, uracil replaces adenine. There it is there, that's the uracil, and no, there's adenine there. There it is, thymine is what it replaces. So now that one there now is in there, see the yellow one. Now what was the reason for that? Okay, I'll mention that a little further down the track when I get on to something else. Okay, the copy made is the ribonucleic acid, that's RNA. The piece of the RNA is released from the DNA and then the DNA closes again. RNA now delivers the data copy to the areas of protein manufacture or the ribosome. There's some of these funny terms, don't let them confuse you. I'm going to try and use layman's terms in some of this, but I'll mention some of these so that those people that might have a little, might have a book at home they want to look up, they can recognise some of these terms. The types of RNA, we've got the messenger, transfer and ribosomal RNA. The messenger RNA, that is a code which goes out to become the blueprint by which our amino acids are going to be compared. Yes, we've got the right amino acid, it agrees with the blueprint. Next one comes along, yes, that's the right amino. No, this is not the right one. Chuck it out and we'll put in another one. And so now, with the messenger RNA, it will be the code that verifies the right substance. Delivers DNA code for making the protein. The transfer RNA, what that does, that is also manufactured from the DNA molecule, and it will go scouting for freestanding nucleotides. And when it finds them, they will latch on, and then it will take it around to the ribosome, here. And then it will connect with that, and the ribosome reads the mRNA and makes the complex protein. It will read what the blueprint says, and looks at what the transfer RNA has brought over, and says, yes, that's an amino acid I can use, and it takes that amino acid, and it then links it with others and manufactures the protein. The protein then goes on to go to the cell and then prepares for the manufacturing of a new cell and cell division. Alright, to read the code correctly, the starting point and the direction of reading needs to be determined. The letter codes are formed by the nucleotides, and there are 3 letters called triplets that make the code for a specific amino acid. Just a summary of what we've just been talking about. Now, in order to read the blueprint, for this code to be read, it requires a decoding machine or a mechanism to extract the information. Now, what I've just been talking about is that very thing. It reads the code, puts all the data in a place where protein is able to be manufactured. And it needs all these things to be in place. What makes the operation impossibly complex is that the machine to decode the DNA is contained in the DNA formula itself. Now you're latching onto that? I know this is probably a little bit much to get your head around at the moment, but have a think about this, because it says that the information about manufacturing the protein needs a device to read the code. The device to read the code is encoded in the DNA. Can you imagine the difficulty that raises for random selection and evolution? Because what it means is this thing is contingent upon this. This depends upon this. And there they are together. And I want this thing's going to evolve, right? And they're going to be having a few tries, having lots of tries to get it to work. But this thing hasn't evolved. And so if this hasn't evolved, it's not going to talk to this, right? And so every time, even if evolution should strike the right formula here in the code, the thing that reads it and makes a bit of sense out of it hasn't evolved. Can't work. It's like saying, Judith, I've lost my glasses. What's my problem? I need my glasses to find my glasses, right? And so this is the problem that DNA has. And so it wants to manufacture the protein. It just might strike it lucky. But it doesn't have the code to read it so it can go and make the protein. Impossible to evolve. God has tied this up. God has confounded the evolutionists unquestionably, uncorroboratively, unequivocally with this technique. He then goes on, this means that the open DNA information, the decoding machine portion of the code itself needs to be decoded. As expressed more simply, well there we go, that's the illustration I used. It follows that such a system must be fully in place before it could work at all. It is said to be irreducibly complex. That means I can't break it down to smaller bits that make it easy to do, right? Let me suggest this. Anybody ever pulled a motor car apart? I remember the first time I pulled an engine apart. Man, I laid every bit out. Make sure I went back the right way, okay? And has anybody ever pulled a microchip apart? All right, we can't do that, can we? All right, and so now that little microchip, many times smaller than the motor, but it is irreducibly complex. You need some really highly specialised equipment to work on these things. Once you've manufactured it, you don't repair it, you throw it away, and you get another one that's been made. So when I say irreducibly complex, what I'm saying is you can't break it down into any smaller pieces and let those little pieces be manufactured and then bring it all together later. It is already as small as it possibly can be made, and it's too complex. All right, let's move on. It could not be possible to have built-in random chance, that is, have a combination of amino acids and see if it works. The evolution of things could not say, well, here's a bunch of amino acids, let's check this out. No, it doesn't work, another lot. And so, a man by the name of Miller, he did an experiment, and he put what he believed to be the gases of the primordial era, where before all things got started, he put these gases together and he was going to make life, this guy, in the laboratory. So he set up his flasks and he put his Bunsen burner underneath, he washed all this stuff, all the tubes down. And what he did, the things that he made, and by the way, he had a couple of electrodes up there and he put a high voltage across it and a spark jumped the gap, which would stimulate lightness. And what he made was 3 amino acids. Yeah, there, he said. I've made life. Now, you can see he didn't come anywhere near it. Sure, amino acids are the building blocks for proteins, just as proteins are the building blocks for cells, just as cells are the building blocks for tissue, and tissue is you. Right? So now, these amino acids that he made, by the way, they would not be able to exist in an environment which was conducive to life. To start with, they couldn't survive in oxygen. And so now that would make things a little bit difficult for us when we want to take our first breath. And so now he was totally amiss with that. And then trying so on and so on. It will never happen because it needs a part of its own code to decipher itself. So which evolved first? The structure code or the decoding machine? There we go. DNA is by far the most compact information storage system known to man. Now here we have, there's not too many more slides there now, so if that's any relief. Here we have a transfer molecule. Now the transfer molecule, here you see a adenine, uracil and uracil here on the end of this node here. And what happens, this transfer molecule, what it has done, it gets the code from the DNA, and then it takes this code and picks up freestanding or free-floating disconnected nucleotides, and they will connect with the transfer molecule. And there they are, 1, 2, 3. You've got a there they are, the transfer molecules there. There's the 2 uracil and the 1 adenine that is there. They then in turn attract their complementary nucleotides, and there they are set on there. That now goes to the ribosome, where this is all processed and starts to manufacture the molecule. Here I've tried to illustrate what goes on using a flowchart. From the DNA, we'll have 3 lots of RNA manufactured. There is the message RNA, the ribosomal RNA, and the transfer RNA. They all go to the ribosome eventually. Now, that word ribosome might be a little confusing at the minute, but when I put this next slide on, I hope it will clarify a little bit. All right, they go to the ribosome, and this is the place where the message RNA is read. The ribosomal RNA enables or assists in the reading of this, and the transfer RNA is the molecule that brings the information to the ribosome so that it can use these amino acids that are contained here for the manufacture of proteins. That then manufactures a protein and then spits it out, and that's used to make a cell. It's a little bit complex, isn't it? And yet we were supposed to believe that this stuff just falls into place.
It is really complex.
Just falls into place, yeah. All right, now that is a frightening looking diagram. I remember when I first looked at it, I thought, oh no, where do you start? Now, have a look at this. Up here, we see this looks like a string of sausages, doesn't it? Now that is the DNA. And you notice this little lengthy bit here. Well, that is where it's been unzipped, and that's where it's been unzipped, and out pops the message RNA. There it is there in that black strip. This one here is another one which produces the ribosomal RNA, or rRNA, and this one here is the transfer RNA made or copied from the DNA here. So we've got 1, 2, 3 ribosomal RNA. Now, that one comes out into what is known as the cytoplasm. Cytoplasm is just a fancy word for space out there, right?
It's a fluid.
It's a fluid, yes. Okay, and so now that then comes out into this space here, and that's the message RNA. That is the code that says we want these amino acids made like this. And from these amino acids we're going to manufacture protein. Now, oops, back we go. That they then will attach themselves to the ribosome. If you have a look at this, you see red, black, whatever that is. There it is, red, black, there's the step, and you got the 3 yellow ones, there's the 3 yellow ones, and then you got black arrow, red and yellow again, a black arrow, red and yellow again. So that little layer has been laid on the top of the ribosome. The ribosome is the machine which reads and manufactures these things. Over here we have the ribosomal RNA. It comes out, this is the cell, this brown bit here is the cell. It comes out through the pores in the cell, and then it comes out to a point where it is accessible by these DNA molecules. Where's the, by the RNA molecules. Where's the DNA in all of this? Where? In the cell. Why isn't it outside the cell?
Because they're the blueprints.
Because this is the blueprint that we want held in the drafting office, is it not? These here, that and that are the copies we send out on the job. We can allow those to go out because if they get lost, we can just go back and get another one. Alright, so all the copies come out. There's the message RNA, and there's the ribosomal RNA, and the ribosomal attaches itself to the ribosome and says, righto fellas, now we're going to read this. We're going to read this. And so it lays it out here, and then along comes the transfer RNA, which is now a little code which says, I want an amino acid of this type. And so it sends it there, and it takes 3 code letters to tell this thing what kind of amino acid it needs. And so now there it is, it attaches itself to this conveyor belt, and that open end there enables it to attach. Notice here that these little coloured pieces here, they're all amino acids. And it will attach itself to that, and it says, yes? Attach itself to that, and this says, yes, we've got a mix, we've got a match, and so it matches, and it sees that this now is the kind of amino acid that it needs. That moves on to the next stage, and the next transfer RNA comes in, and it hooks onto the conveyor, and it has its load tested as well, and so they move on their way through the conveyor. And this little message here says that the bond formed between the amino acids form a protein molecule. So these amino acids now coupled together by an atomic connection. Alright, you can have covalent bonding, or you can have ionic bonding and various other things. People that have had a little bit of a look at physics will know what we're talking about there. And so now we now have all these amino acids formed. By the time they get to the end of the conveyor, we now have proteins formed. And these proteins now are used by the cell to manufacture the new cell. Now in a fetus, we need to have tissue which makes all the different bits. Eyeballs, ears, hair, blood, bones, etc. Right? There are different kinds of molecules. Just as when you're building a house, you put bricks on the outside and you put gyprock on the inside. Some people have rock on the inside and some people have something else on the outside. But anyway, you can see that whatever is required in the body, the cell, the DNA, has got the code there that says, this new cell that's being manufactured, it's not going to be skin, it's going to be an eyeball. Alright? And it's got to be different. And so now it's all encoded by intelligence. It didn't happen by accident. Isn't God wonderful? He has confounded the evolutionists unquestionably. And this thing here is, look, if anyone starts expounding evolution to you, you just say, well, please explain the DNA molecule to me. And you'll stop them in their tracks. One of two ways. Either they will not be able to explain this from evolutionary standpoint, but they may not understand how the molecule works anyway. And so now what we have is this wonderful complex setup inside the cell where we have the DNA. DNA produces 3 kinds of RNA. And the RNA, the ribonucleic acid, now has 3 different forms. Transform or transfer, ribosomal, and message. The transfer RNA goes out and collects amino acids which then, according to the code that is on the molecule, it will attract the correct amino acids. And then from that, it will then go onto the conveyor belt, and the RNA, which then educates the ribosome to produce, to be able to read the message RNA, then that message RNA can now confirm, yes, you've got the right amino acid. Those amino acids on the conveyor belt all join together to form a protein. And then the proteins in turn are used by the cell to manufacture the new cell. Marvellous, wonderful piece of engineering. And it is at the microscopic level. Non-coding molecules in DNA. Now this is has thrown a bit of a spanner in the works that has tended to make us things a little bit confusing. The RNA contains chemical regions known as exons and introns. And the exons carry the actual code for the placing of the amino acid. The introns are non-coding chemicals interspersed between the exons. At a specific point in setting up to read the RNA code, they are removed to leave a clean series of letter codes. Now, what we've said is this transfer RNA is quite clear cut. It just goes in there and it shows the nucleotides, and the reading of this seems so easy, and okay, that's quite straightforward. But what we notice is that there are other elements involved here. This one here, introns, that there are 97 or 98% of all the molecules in the DNA, listen to this, are non-coding molecules. Non-coding. Now that means that this thing not only has to manufacture these from the information that it's got to sort through a whole ring of stuff to find the thing it needs. It's like finding the proverbial needle in a haystack. Now, to do this, an elaborate machine called the spliceosome is assembled on the intron. It cuts out the intron and splices the exons together to form a readable code. The complexity of this operation becomes apparent when we appreciate that the splicing must be in the right direction and the letter codes spliced together in the right sequence. It has been, well, there we go, I've mentioned that before. Now, there we have 1, 2, 3. They are your coding bits of data, the letters A, G, T, and C. That's that. Oops. These here, 1, 2, 3. They're the exons, the coding data. X and Y are the introns, or the bits that are non-coding. Never mind that I've got the non-coding bits in the minority. I'm simply just illustrating in a simple form what this thing actually does. The spliceosome comes along and attaches itself to all of these introns, or these non-coding bits of data, and says, right, we don't need you, out of the way. There's the bits of code I need. And then it says, all right, so it pulls those out, and I'm left with 1, 2, 3. All right, and I'm left with the code letters. And then it brings them together, and you get those 3 nice little codes left.
And that's supposed to happen randomly.
Yes, it is absolutely amazing. Not only did God make the whole thing complex, but now he goes and throws this in to really make it look difficult.
Amen.
And so, look, when you're doing a job, what do? You clean up first, get rid of all the rubbish, and then you set about to do your job, don't you? And if you do a lot of bit of rubbish, you get rid of it and then you carry on. And you find you work nice and comfortably, and it goes quite smoothly. And this thing here has got a whole lot of debris. 98% of the whole thing is, I'm not going to say rubbish, but, you know, stuff that doesn't seem to contribute. Well, what are vestigial organs? They are bits of the body that we once understood to be relics of evolution. My appendix is, I don't need my appendix anymore. Gives a little bit of pain, rip it out, right? No, we don't need that. Tonsils, etc., etc. You know, there was a time when they thought that there were 100, could you imagine? 100 vestigial organs. Unnecessary relics of evolution that our body is just housing, which doesn't do anything. Now, you know, with our advancing knowledge in about anatomy, that number is now no longer 100. It is now reduced to a very small number now. And so I hope that we wake up to ourselves and say, well, you know, we were wrong on all those. Maybe these last few that we don't understand, maybe they're not vestigial organs after all. All right. Could it be that these introns are vestigial bits of DNA? Nonsense. There's not a lot known about what the introns do, but there are a few theories and they're still working on it. We're learning more and more about DNA, and I believe that as we grow further in our knowledge of DNA, we're going to become more firmly established that the whole of creation was made by intelligent design.
Amen.
So we have an intelligent designer. Now I'm just going to summarise a few things here. So the DNA module could not possibly have evolved from a random chance of hitting on a working assembly. If one should choose to argue that DNA did evolve, chemicals are one thing. But where did the undeniable code come from? Again, if DNA did evolve, at what point does the living organism become alive? You know, no one can define life. The closest I've ever come to it myself, I imagine it this way. A computer, right? A computer does some wonderful things. The circuitry in there is like your body parts. And there's a memory there, which is like your brain. There's a processor, which is like your reasoning, as it were. But mind you, there are some distinctive difference between the way a machine thinks and the way a man thinks. And the electricity, like this box, does absolutely nothing until you switch on the power. And I kind of imagine life as something like that. Life is the energy source that must come from somewhere that animates all of us. What's the difference between a live person and 5 seconds after that person is dead, they're on the floor? What's the difference between the two? How do we measure the spark of life? I don't know. We can measure electricity in a circuit, but that's not life, is it? But it just illustrates how something may be alive. The code can only be the product of intelligent design, and intelligent design speaks of a master designer. I praise thee, for I am fearfully and wonderfully made. Marvellous are thy works, and that my soul knows. Very well. Praise God for DNA. Praise God that He is showing us and giving us another affirmation to His wonderful power and to His existence. And He is strengthening His people. When someone comes to you and says, evolution, you know that these poor folk, they're missing something. Now you can share something with them. And look, if you want some more information on this, I just got this out of the high school biology. Just for the sake of the camera, the comment was that cell division is a microcosm of the division of the Father and the Son. And I think, look, I think it is just the way God works, is it not? That when the sperm and the ovum come together, that then there's that first division. The first part of life, God is giving us an illustration of what He did right back at the beginning. Right at the beginning of a new life, He did at the beginning of all life. Just for the sake of those that are looking at the video, the comment was that with the complexity of things, that Charles Darwin would not agree that his theory was true. He would confess that he has made a mistake because of the complexity of things we see today.
Amen.
And appreciate. Any other comments?
No.
Yes?
Before you finish, please can you sing 255 when you finish?
255, eh? Yes, I think we could probably do that.
Thank you.
Yeah. Okay. Well, look, thank you very much for your attention. I thoroughly enjoyed doing that. I hope I didn't bore you too much. I didn't see too many people nod off. Praise God. Look, I tell you what, I said to God, help me do this, you know. And He does. He's helped me tremendously with some of the deliveries that I do, and I really praise Him because I know it's not me, it's Him. And thank you, Lord, for that. And I pray that each of you now will have a better understanding. And look, don't just stop there. Have a look at, get some of these, go down the library, you can hold the kids' biology book and go through some of this stuff and learn about cells and DNA, and it strengthens your faith. It's really good stuff. All right.